We saw the design and looked at it and thought, wow, this is something that's going to be here for many, many years, and we really wanted to have Multiplex's name against it, that we built Bunjil Place. All the veneer that has been used in the project has actually come from one tree. So in the process with the architects, when we were selecting the veneer, we headed out to the factory in north of Melbourne, which in Campbellfield, and we were selecting through the black butt veneer, and the supplier of the veneer actually said, hang on a second, I know of a tree that's been sliced that sits in Queensland that has about 4,500 square metres available. How about I get that sent down and we'll see if it matches the project. So the supplier sent the veneer back, and we headed back a week later with City of Casey and FJMT, the architects, and we selected the veneer, and it was a perfect match for the project. So I don't think ever again we'll have a project that has one single tree used for all of its timber veneer. So the theatre in particular and the studio were supposed to be what is called in situ concrete walls, where formwork is put in place and then cast. Multiplex had decided that a quicker way of building would be do it all out of precast concrete, which means all the concrete elements are cast off site and then assembled and erected on site. This presented quite a big challenge for the engineering team and the architect team to actually document it as fast as we needed it documented, and then also make it engineeringly work. Given that the fly tower is 18 metres high, we were driving for 18 metre high concrete precast panels, which ended up being engineeringly impossible, but we split them to two 9 metre panels. The engineering and the construction sequencing to actually make that occur, if you actually were fortunate enough to drive past early on in the project when the temporary steel was sitting on the back of the fly tower, you would have been able to see the amount of temporary steel that we actually had to install to make the precast be installed. The roof of the building is structural steel. It's very much a shame that we've covered it in. The hours of engineering that was been undertaking to actually make it work. There's three-dimensional curves, there's rolling members, there's members that have 8 different pieces of steel that are connecting to one piece of steel. But how it all starts is the engineering firm TTW, along with FJMT, come up with their initial design, and then they do a detailed design which they detail out every single connection member. That then is sent off to our structural steel contractor, who then 3D models the steel and makes it all work, so to speak, coming together with all the dimensions and the loading elements and the connection details that he's been given. From that 3D model, he then is able to produce 2D drawings that allow a fabrication to occur. So every piece of steel has a drawing to it. We're probably up into the tens of thousands of drawings for the steel roof. So it's quite a task to make it come together. That's just actually prior to it coming to site. Then it comes to site and we undertake an erection sequence and an erection methodology, so actually how it's going to be installed. And then with cranes and mobile cranes, high access reach equipment, the men or women, but it was all men on this occasion, get up and follow the installation sequence and install the steel. So we do concrete crack tests. So virtually every element of concrete that's poured has a little solid cylinder that's taken from that pour, and we, in a lab, they test the concrete for its compressive strength. This allows us then to move forward, putting precast and other elements up onto the building. We have to achieve a certain crack test result, and it's measured in an MPa. Other tests we do the weld testing. So as I was talking about earlier with all the structural steel, we do non-destructive weld testing. It's like a little X-ray machine that they go up and they test a certain percentage of welds to make sure that it actually the weld is actually true and proper. There's a number of other different tests that we do throughout the course. We'll do acoustic tests, but yeah, the 800-seat theatre is isolated from the other two buildings, so to speak. The other two buildings that we describe is the studio or the library. They actually don't touch each other. So the concrete structure of the theatre is not attached to the surrounding floor slabs acoustically. So structurally it's attached, but there's acoustic isolation mounts between the concrete structure on the outside of the theatre and the concrete structure of the theatre. So they're a Embleton mount. I believe they came from the US, and you unfortunately can't see them because they're up in the ceiling space and you can't walk out and have a look at them, but that's how the acoustics are dealt with, in that the buildings are separated, so to speak. Okay, the glazing that stretches across the front of the building, the name for the glazing, we call it, is the F1. That's just the description on the drawing, so to speak. But it's laminated glass. It's 2 layers of 14mm glass. The glass is what's called low iron to make it clear. It was manufactured in China. It's supplied by a company in Melbourne called Viridian Glass. It's curved, which is a very unique element to the building. The curve it's a 3-metre piece of glass. There's about 4 to 5 pieces in a vertical run and about 15 wide. So all the curves are the same. Some of the glass, as in the radius of the curve is the same, but the sizes of the glass can vary. It's manufactured pretty much how normal glass is manufactured, but 2 layers of glass that they laminate them together with an interlayer that's structural, so that if someone cracks it, so to speak, it actually doesn't shatter. It should crack, and the interlayer will hold it together. The fins, there's 13 fins that you can see that actually hold the glass in place. So the architects and engineers are actually using glass as the structural element to hold the glass in place, which is quite unique. It does occur around the town in certain different Apple stores is another place where you can see a different type of build-up, but in this instance, the fin is actually the structural element that's holding the glass up. The timber grid shell that sits within the foyer, has to be the defining element of the building. It's came from Germany. It took roughly about 14 months to procure, and what I mean by procure is by the time we search the world for a supplier and someone that can actually manufacture it, then we place an order with them, and then we have to design it with them and the architects and engineers involved in the project to then have it delivered on site and installed. So it's been quite a feat, but it's gone in. There's over 1,000 individual pieces of timber that have to be assembled one by one and bolted together and screwed together. There's over 1,000 pieces of plywood that sit up in the ceiling space that you can't see. You can see, but you can't see the difficulty that is associated with those pieces of plywood. The heaviest piece was around 3 tonne. There was a number of pieces with 3 tonne, so obviously that was installed via a crane and then slung into position and then fixed off with a number of bolts that you can't see anymore because they're tucked into the timber and then hidden up. But probably one of the most unique parts of it is the bottom of the grid shell that you can see. It's made up of individual pieces of timber. They're actually called lamellas. There was over 100 pieces of lamella that are joined together to actually make the curve in the bottom. So the smallest thickness was 13 millimetres. So they actually lay pieces of timber together and then glue them together, and then just prior to the glue going off, they bend them into the shape, and then the glue goes off and holds them in place. But yeah, it has to be the greatest achievement because there's no other structure like the structure that we're looking at Bunjil Place in the world. The lamellas need to be quite small so that when they put them together and glue them together, while the glue's setting, they then use their machine to bend the timber into its shape. The thicker the timber, the less radius that they can bend it into. So the tight radiuses out in Bunjil Place are actually the tightest that Hess have ever actually constructed. That Hess actually described Bunjil Place as grid shell as the most complex that they've ever completed. The reason for that being is it's actually 2 layers. There's an upper layer and a lower layer. So when you actually stand and look at the grid shell, you'll see that the base, you have the members that freeform and flow up into the roof, but there's also an inner layer there's a secondary layer, which made it very complex for Hess to make the connections to work and the engineering behind it. But